Hi everyone. This lecture is both for the full-time students and the part-time students. For the full-time students, this part, there's just an additional part at the end on data security here. And for the part-time students, all of this is new because we were supposed to have a lecture on this stuff on Monday, and because of load shedding or some kind of power cut, we were not able to have our lecture. So as a result, we have this video. Okay, so in this video, I'll just discuss a few things. The first one is frame the difference algorithm. Okay, so the frame difference algorithm, that we'll discuss that first. The second thing we'll discuss is something called error detection and correction. The third thing we'll discuss is an algorithm for data security. So the full-time students should have done this, but they didn't do this. Okay, so in other words, if you're a full-time student, don't disregard this video. You can still learn something that is examinable, which is the stuff on data security. For the part-time students, you're going to have to know all of these concepts as well. Okay, so what are we going to learn? Well, this frame difference algorithm is a type of encoding mechanism. And you know what encoding is from the last lecture. Encoding is basically changing something from one format to another. That something can be a piece of text, it can be a video, it can be a music file or whatever. But we're just trying to we're encoding it to translate it from one format to another. Usually the format that we're interested in encoding something in is in binary, and that's because memory in a computing system is organized in binary, and so transforming text input or music input in the form of frequencies or whatever else into binary is the rough idea. Having said that, in computer science, sometimes we also want to convert from binary to hexadecimal. That's also, in a way, an interpretation of encoding. Okay, and we, in some applications, for example, in web design, you often have to translate, let's say, colors into a hexadecimal encoding so that we represent different colors efficiently using hexadecimal. So this is an example of encoding, but in this particular lecture, we'll look at the frame difference encoding. It's also denoted as FDE, and this encoding is a very basic encoding where you look at a video file and you try to look for ways of encoding that information by looking at consecutive frames. So a video is made up of multiple frames, and every consecutive frame we want to be able to save what we store. In other words, store less based on the difference of these frames, and that's the idea behind this encoding. So I'll define it for you and give you an example of that. The second thing we're going to look at is error detection and correction. Well, what is error detection and correction? It's based around something called a transmission error when we move data from one place to another. And this transmission error, we try to reduce it by thinking of clever ways to be able to identify where particular errors could have occurred. So the big idea behind error detection and correction is that, and what I'll do there is I'll show you an example of a message being sent from a sender to a receiver, and I'll show you using a theorem that it turns out there's the task is somewhat hopeless in that there's always a non-zero probability of an error going undetected from the sender to the receiver. And there's a theorem around this, which is a bit of a depressing outcome, right? It says that sometimes you can have a valid message turned into a different valid message transferred from one to the other, and there's basically no way we can actually determine that it actually occurred. But it's a wrong valid message. So when I say a valid message, I mean a message within the same scheme as the other messages are, but it's not the message that the sender intended for the receiver to get. So that's the idea behind that. So we'll look at that theorem, and I'll show you some stuff about Hamming distances and parity bits, to do this particular task. And then the final thing we'll look at is data security. I had a lot of plans for data security for this course after I've restructured it, and one of the plans was to show you the Caesar cipher, the Affine cipher, the RSA cipher. In other words, giving you a good indication of the symmetric and asymmetric ways of encryption. But because of time, there's so many things to explore in first year computer science. Because of time, I'm only going to look at one particular one, and that's called the Caesar cipher. So the Caesar cipher, that's what I'm going to show you. But yeah, having said that, nothing stops you from learning more. Although the only one that I'll examine here is the Caesar cipher. Hopefully, maybe if we can, it's a trade-off, right? If I teach you something, I have to take out something else. So it's very difficult to see what is important. So this particular section on data security, you'll only learn one thing, but just bear in mind there's lots of other things to learn. Okay, so that's in terms of the learning outcomes for this particular one. So let's get straight into it. Let's start with the frame difference encoding. So the frame difference encoding algorithm. Okay, and also, I don't know what your learning preference is, but I believe that you should take your own notes. And as I'm presenting these ideas to you, if you're not playing it in double speed, then you have the opportunity to rewrite some of these things and take down notes from what I'm saying to help you understand these things better. Okay, so the frame difference encoding, Frame difference encoding, FDE, is a technique used in video compression that removes temporal redundancies between consecutive frames. Okay, so for those of you who don't know what these words mean, so the frame difference encoding is a technique. So this is it's a method used in video compression. So this is to make videos smaller. In megabytes, kilobytes, by removing temporal redundancy. So what does temporal mean? It means over time. Redundancies means data which is repeated. Between consecutive frames. Consecutive frames means the frames are right next to each other. That's what it means. So the algorithm that we use here is the frame difference encoding algorithm to do that. So how does it work? So let's see, how does it actually work? Okay, so let's start off with frame 1. So in a video, you have different frames. You have frame 1, okay, you get frame 2, and you get frame 3. So frame 1, frame 2, and frame 3. And obviously these frames are consecutive, which means that they're right next to each other. So you have frame 1, and that's next to frame 2, which is next to frame 3. Frame 3 is next to frame 4. Frame 4 is next to frame 5, and so on and so on. Okay, so I'm going to have to just draw. Obviously, you can have thousands of pixels, right? Millions of pixels. But in this example, because I don't want to draw millions of pixels, I'm just going to draw a little grid with it's a 3x3 frame, which means that there's 12 pixels. 1, 2, 3, 4, 5, 6, 7, 8, 9. Sorry, there's 9 pixels. So obviously 3x3, right, is 9. So there's 9 pixels. This is the first pixel, second pixel, and so on. So these pixels can take the form, this is what we call a binary image. And a binary image can take each pixel can take the form of a 0 or 1. A 0 being white and a 1 being black. So you can think of it as the absence and presence of data. So I'm going to color this in. So this is an example of a 1. and the empty ones are examples of zeros. And you can think about how the encoding actually works in terms of the mathematics behind it. But what I'm going to show you here is the analogies of there is something or there isn't something, that kind of idea. Because I want you to try to figure out the math yourself, right? So it's just, there isn't really difficult math here. It's a subtraction. But how does that subtraction interpret to the zeros and ones? So think about that. It's a first year problem. Don't overthink it. So let's have another one here. So maybe this video is like the Lord of the Rings, or I don't know, other movies that you like. Doesn't have to be movies even. It can be clips on YouTube, anything. Can even be a TikTok. Can be anything. Okay, great. So that's what we have so far. This is the movie. So what we do in the frame difference encoding is we store the initial frame exactly the way it is. We store this exactly the way it is in memory. So now what I'm drawing at the bottom now is what we're going to be storing. So we store this exactly the way it is. Okay, so we stored it exactly the way it is. And then, what do we store next? Well, we can store the whole frame 2, right? But instead of storing the whole of frame 2, let's only store the positions on frame 2 where there's a 1, okay? And if we do that, then in the original frame 2, which is this one here, how many things would we need to store? 1, 2, 3, 4, 5. We'd have to store 5 ones, okay? But instead, if I rather store the difference between frame 1 and frame 2, so let's store frame 1 minus 2, then I'll end up with this. Because the only difference here, I'll draw it for you just once so you can figure out what's going on here. You see, because this cell is the same, it has a 1 and this cell has a 1, then I interpret that as a 0. Okay? And similarly, it's because this is the same as this, I say that there's no difference, so it's a 0. Here, there's no difference, so this is a 0. Here, there's no difference, so this is a 0. Here, oh, they're different. This is a 1, and this is a 0. And so, if I store the difference, I can even say storing the absolute difference, then you'll have a 1 here. Okay, if you don't know what absolute means, you can just Google it. It just means that you are, if there's a negative, you're ignoring it. So it's an absolute difference. Okay. Right, that's the big idea. So now from storing 5 ones in frame 2, I store 2 ones in frame 2 because I'm trying to capitalize on what's similar. Okay, then let's look at the next one. So I'll switch back to black. And what do I store here? Well, I'll now look at the consecutive frames, frame 2 and frame 3. So there I wouldn't store anything because this is the same as this, so this remains as a 0. What will be the next one? Oh, there is a difference. So here's a 0, here's a 1. So that means I have to store something here. Okay, so let me just quickly Control Y. Okay, so there would be a difference here, there'd be a difference here, there'd be a difference here, and there'd be a difference here. So from storing 1, 2, 3, 4, 5 ones, I only now store 4 ones in the original. So how do I get the compression ratio? These are the questions that you have to think about. How is the... Okay, let me write this at the bottom. So I'm just trying to provoke your thinking. So these are the questions you should always be asking yourself. But how do you go down? I can't go down. So what do? I need a new page. Okay, so these are the questions you should be asking. So how do I calculate the compression ratio? How do I calculate a compression ratio? And you can think of other questions by thinking about what did I have to do in the other questions for encodings and how is it related to this. Right, so there's lots of things to talk about here, but I'll leave you to think about these things on your own. So the next thing I'd like to teach you is error detection and correction. This is the second topic I wanted to speak about. And the basic idea behind error detection and correction is as follows. Suppose I've got a grid And this grid has numbers inside of it. I'm just making up stuff. Okay, this is the sender. This is the person who wants to send the message. And they send the message now to the receiver. One, two, three, 1, 2, 3. Oh, there was no space there. 1, 2, 3. I'm sorry, my art's I'm not very artistic with drawings. And it's so strange. My dad and my brother draw so well. They do these beautiful works of art, beautiful paintings. But yeah, I can't draw. At least I got the music gene, maybe. I don't know. But I definitely don't have the art gene. So, or maybe I need to try. I shouldn't really say I can't do something until you try, right? I mean, this is true for everybody. So what happens here in electromagnetic signals? We sometimes have to deal with electromagnetic interference. Okay, so when you're sending something from one place to the other, you have electromagnetic interference. This could be anything. It could be software errors. It could be physical damage to hardware. It could be anything. Someone could have written a piece of code that doesn't do a very good job for solving the problem. It makes a mess of the data. You'll see this can happen when you are dealing with low-level codes like assembly, which we'll talk about later on. There could also be physical damage. Maybe that part of RAM is a bit damaged. The few bits of RAM are dead. For whatever reason, there's a family of dead cells of memory, and they need to they always mix up the bits, so they unreliably store information. It could be anything really. It could also be the solar radiation from the sun, right? The sun can flip bits. It does it all the time actually on your cell phone. While you're walking around, the sun is actually causing the bits on your cell phone, which are stored in memory, to flip around. And this has to do with electromagnetic radiation from the sun interfering with how information is stored using transistors. Long story short, the sender sends information to the receiver, and the receiver sometimes gets the whole message or sometimes gets the message with little errors in them. And the question now is, how do we identify those errors? So this is what the receiver actually received after the sender sent the information to it. And I say it also. This doesn't have to be a person. It can be it as well. It can be a piece of. You can think of this process happening inside of the same computer. So maybe information is being moved from one part of memory to another part of memory. Information is moved from one device to another. Information is moved. It's moved all the time. I don't know if you've noticed, but you might, if you haven't, then you will notice in subsequent lectures that sometimes we move things around because maybe we want to, and you'll learn a lot about this in Richard's class on data structures and algorithms. We're always moving information. So data structures and algorithms. This is a very important course. And if you want to go and work for Google and Microsoft and all of those big tech companies, Netflix, Apple, then this is the course that you really need to do well in. Because this is the course that they ask you questions about when you go on interviews to those companies. Those FANG companies, they often target these specific coding questions to test your ability and be able to solve problems. So here there's lots of moving information around. So for example, you can store information. This is called a tree data structure. So this is just a normal tree. There's no ordering on the nodes, but I'm just making stuff up here. Okay, so let's say then you want to swap 3 and 2, right? So then you can swap these two cells, and if you do that, you're moving the 3 to the top and the 2 to the bottom. So some kind of swap occurred. Oh, that didn't work. So this 3 and 2 are swapped. Okay, so this happens a lot in algorithms and in memory management, in operating systems. Information is always moved around in memory. Okay, you'll be surprised how often that happens. But anyways, this is the basic rationale, right? So there is some interference, and that causes the information to change. So this is also called a transmission error. And a transmission error occurs when data received at the destination differs from what was originally sent. That's called a transmission error. So, like I said before, there's a theorem that actually is a bit of a depressing theorem. It is called the error detection uncertainty theorem, and I will write it down for you here. And this is actually proven in one of Shannon's papers. So let M be a set of all messages over a channel, be a set of all messages over, and V, which is a subset of M, be the valid messages by a protocol. So the protocol can be something like the English language, right? There's certain words that are part of English, and there are certain words that are not. So for example, this word, the protocol of language in English grammar says that this is a word. This is not a word, sorry. Okay, this is not a word, but this is a word. So the protocol determines what is a word and what isn't. So maybe the protocol can be that all of the words must belong to a particular dictionary of words for it to be a valid word. Okay. So an error detection method is a mapping. So it's F, okay, from all valid messages to some kind of code word, where C is a subset of M, are code words. So with any non-trivial scheme, when a scheme, in this case, a error detection scheme, the probability denoted as P of undetected, so the probability, that's what it's denoted of an error turning a valid message into another code word undetected is positive. This is 0. Okay, so this is the theorem, and it basically says that the probability of a message going undetected is always positive. There's always a chance. I'll write this in a different color pen. So there is always a chance, non-zero probability. So that's what a chance means. There's always a chance of an error going undetected. Okay, that's what it means basically, and it's actually quite quite a depressing outcome but it makes sense, right? It makes sense because if you don't have access to the original message, then that original message could have turned into anything, and one of the anythings could have been something that you could have expected, and it makes a lot of sense. I mean, this is it's a very intuitive theorem. It's a very bad result, but it is one that we have to accept. And once we accept it, we can start making some constrained situations where we can detect errors. And hopefully, one of those constrained conditions of where we can detect errors will be a real life mechanism to help detect errors. So let's now look at this from a different perspective. So suppose that you suppose you had access to the original message. Let's look at this from that perspective. So suppose, obviously you never will, but suppose that you have access to the, suppose that you have access to the original message. Okay, then how would we be able to determine if the sent message is different from the original message? You can simply compare them. Okay, you can say, well, if A is equal to 1011 and B is equal to 0011, and this is the message that I was sent, and this is the message that was received, then if I have access to the sent message, which is this one, I can just compare them string by string, right? I can say, okay, so this here is different from that there, so there's one difference. This here is the same as that there, so that was sent correctly. This is the same for that one there, which is sent correctly, and this is the same for that one there, which was sent correctly, which means that A and B differ by one thing, which is the first bit. We can put this more formally inside of a mathematical definition, and this is called the Hamming distance. So let's quickly then go to our black marker and write down the definition for the Hamming distance. So the Hamming distance, given two strings A and B of equal length n over a certain alphabet, the Hamming distance denoted as HA of B is defined as the number of positions at which the corresponding symbols are different. Okay, and we can denote it as H of AB is equal to the sum, right, from the first bit to the last bit n. It's some kind of function involving the corresponding bit I from the initial string to the corresponding bit I to the received string. Okay, so then where AI and BI are the ith element of strings A and B respectively. The function AIBI is defined as, so basically the function will output a 0 if they are the same, because we don't count it if it's the same, and a 1 if they are different, because we want to count the number of differences. So it will be the function IBI is either a 0 if A is equals to BI, if AI is equal to BI, and it'll be a 1 if AI is not equal to BI, and that's the idea. Okay, so for example, if we go back to our first example here, what would be, so the first delta here will be a 1, the second one will be a 0, then it'll be a 0, and then it'll be a 0. So the answer would be h of a, b is equal to 1. So they are different by 1. And this Hamming distance, the reason why it's called a distance is because it tells us how many changes do we need to get from one string to the other. Okay, so what we discussed so far is not realistic, right? So I'm going to write it in red. It's not realistic because we will not have access to the original string. Okay, we will not have access to the original string. And so we need a more clever method to do it. So the clever method is called, is doing parity checks. So let's define what a parity check is. And once we do that, then we'll be able to look at what the clever method actually does. Okay, so let's begin. So what is this clever method? The clever method involves something called a parity bit. So let's look at what a parity bit actually does. So let's say this is the definition, DEF, of a parity bit. Okay, so what is a parity bit? So a parity bit denoted by P is appended to a binary message to ensure a specific parity. Okay, so what is a parity? It means even or odd. So that's what a parity is. In the count of ones. Okay, including P itself. That's important, right? So it has to include P as well. So the parity count in itself is counted against the ones to make it either even or odd. And we're going to look at it as even. Okay, so it's computed. So the parity bit is computed as P, which is equals to sigma from the first bit to the nth bit, counting up all of the ones, and then you modulo 2. Okay, where BI represents each bit of the original message n. Okay. Right, so let's calculate some parities. So if I have a message like this, and there's 1 0 1 0 0 1 0 1 1 0 1 0 and 0. So this is the same example from before, and because of electromagnetic interference and software damage and software errors, we end up with a changed message. So now we have 1 0 1 0 0 1 0 1 1 0 0 0 0 1 0 1. Okay, so my sender very cleverly included a parity count, which is the first corner bit. Okay, and that parity made all of the ones even. So if I look at the ones, if I count them up, I get 1 2 3 4 5 6 7 8. Okay, there's 8 ones, and there's 8 ones, which including this one, it's 8 ones, right? And this is my parity checker. So if I just make it red, just so you know. Okay, so that's my parity checker. So assuming only single bit errors could occur, the resulting message by the receiver, the resulting message from the receiver, which is on this side, could have only, should be able to look at this bit, which is this bit here, should be able to look at this bit and then check the number of ones. So they're going to count now the number of ones. I'll use a different color. So that's 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Right? So there's 6. And if I count the parity bit 2, I get 7. So the sender was expecting an even count of ones, including the parity bit, but it got an odd count of ones, including the parity bit, which means that there must have been an error in the message. So now, where's the error? That's the question. Well, using our Hamming distance formula from before, our delta function would have given us a 1 for this particular component. Oh, I meant to do this. Our delta function would have given us a 1. The delta of AI, BI, would have given us a 1 here because they are different. And we would have known immediately where the error is. But because we don't have access to the sender's message, there's no way for us to calculate that delta. So then the question is, how can the receiver find out where the error is? How can the receiver find out where the error is? That's the question. Yeah, so how can they detect it? How can they detect where this error is? So if there's an even number of error flips in the data block, just to put a total disclaimer there, if there is an even number of errors if there's even number of errors that occur here, so if an even number of errors occurs here in this transmission line, then there will always be a even count for this parity check, all right? Because it'll change. I mean, maybe there were 8 ones before, 1, 2, 3, 4, 5, 6, 7, 8. If let's say 2 errors occur, then there'll be an even count of ones again. There'll be 6 ones. So you won't be able to detect it. But if there's an odd number, then we'll always be able to detect it. But we might not be able to correct it. So how do we correct the error? So it turns out that there is a way to do it. There is a way, so I'll write it in green because it's pretty exciting. It turns out that there is a way to find out, to not only detect it, the error. Okay, because here we could detect the error. We knew that an error occurred, right? But we didn't know where is the error. Here it is, right? But we would only know that by calculating the Hamming distance, by having access to the sender, but we don't. So where does the error occur? So there is a way to not only detect the error, but also to correct it, which is very cool and exciting. Not to mention, you need so little information to actually do it. Okay, so that's the topic for the next part of this lecture. I'm going to go to I'm just going to try to get another clean page, and the name of that particular mechanism is what we use today even. It's called the 1511 Hamming code. The 1511 Hamming code. So this is what we're going to talk about now. So the idea behind the 1511 Hamming code, and you'll know why it's called the 1511 Hamming code in a second, is by using these parity checks and putting them in strategic locations so that we can find out where the error actually occurred. And we just do 4 tests. So that we do test 1 for the first parity check, You do test 2 for the second parity check, test 3 for the third parity check, and test 4 for the fourth parity check. In test 1, okay, I'm just going to draw this out so I can write it more fluently, right? Okay, let me try to draw a bit smaller. 1, 2, 3, 1, 2, 3. 1, 2, 3, 1, 2, 3. 1, 2, 3, 1, 2, 3. I'm just trying to draw this for you. I don't want to waste everybody's time. Okay, so these are the 4 tests you need to do. So here they are. Okay, so to do the 4 tests, we firstly strategically put a parity check in a particular position for each of these tests so that we can test a particular segment of the matrix, right, of the 4x4 matrix. So here we can put the first parity check that we put is here. And this parity check is responsible for checking the parity of this column and this column. Right? The next parity check, we put it over here. And that's responsible for checking this part of the matrix and this part of the matrix. The third parity check, we put it over here. And this is responsible for checking this part of the matrix with this part of the matrix. And the fourth parity check, we put it over here. And that's responsible, as you might have guessed it, you can see a pattern for checking this part of the matrix and this part of the matrix. And by doing these 4 checks, we can actually then triangulate where exactly did the error occur. So before we could just see if an error occurred, now we can actually find out exactly where the error occurred. So write this in your books because you're going to use it now, right? Let's look at an example. Okay, suppose that you were given the following message. Suppose you were given the following message. So this is the following message. So 1 like that, 1, 2, 3, 1, 2, 3. So you got 0, 1, 0, 1, 1, 1, 0, 1, 1, 0, 0, 1, 1, 0, 1, 1. So the question is there an error in this message? And where is the error? Correct the error. Okay, so these are the 3 questions. So the first one is there an error? Where exactly is the error? And then correct the error wherever the error is, if there is an error. Okay, so how do we do it? Well, you're going to use your 4 questions. The first question you're going to ask is, looking at this particular bit, I'm going to check the parity for those 2 sections. So I look at this bit. Okay, let me then just take another color. So I'm going to look at this bit. Is the parity for this, where am I looking now? Well, I have to look into this column and this column and count the parity and check the parity to see if it corresponds to the bit. So there is, so this is, obviously in this case we're assuming there's only one error that occurred. Okay, so we have here 1, 2, 3, 4, 5, 6. So there's 6 ones. Is 6 an even or an odd parity? It is even, so that is correct. So this is correct and this is correct. Right, now we're going to look at the next test. The next test says that I'm going to check that bit and then see if it is an even or odd parity, and then from that we'll know if there's an error. So now we look at this one, and we're going to see this column and this column to see if we're going to check the parity to see if it corresponds. So there's 1, 2, 3, 4, 5. Is 5 an even or an odd parity? It is odd, right? Which means that an error could have occurred in this column or in this column. Okay. Having said that, we've already checked the last column, so we're gonna assume that it's correct, but we can't. Let's first let's first see where the error could actually be. So I know more or less for sure that an error occurred in this column. But which one of these cells? So the error occurred here. But which one? Okay. Which cell? Okay, so I'm just going to say no and no. All right, now we're going to check. I'll use a different color of blue. Oh, let's use purple. Okay. I'm going to check now this one, and this is responsible for checking this row and this row. So 1, 2, 3, 4, 5, 6, it's 6, which means that this is correct and this is correct because it's odd, it's even. So then finally, the last way I'm going to check is, what color should I use here? Green. Yeah. I'm going to use this one. I need to check then the last test is this last test 4, which says you got to check those 2 rows. So it becomes, let's count. It's 1, 2, 3, 4, 5. Oh, again, we have an odd parity, which means that there was an error. So where did the error occur? Well, looking at this, we can see that this here was verified as correct. So we can ignore the other X. This was verified as correct. The only place that it could have occurred is where we were certain that there was an error that occurred. And we were certain that in this particular column and this particular row, an error occurred. And it would have had to have happened at the intersection of those two, which will be the 0 over here. So that means that the error actually, if we know exactly the error occurred here. And so the first question is there an error? Yes, there is. Yes, there is an error. Where is the error? So it's column 0, 1, 2. So it's the matrix at position row and column. So I have to do the row first. So it's going to be 0, 1, 2. It's at position 2, 2. Okay. And then this is the row and this is the column. Remember, a computer scientist starts counting at 0. So 1, 2, 3. Okay, and then if to correct the error, then we're going to have to correct the error. So we re-give the matrix with the error corrected. So it's 0, 1, 0, 1, 1, 1, 0, 1, 1, 0, 1, 1, 1, 0, 1, 1. And that's the error. We corrected it. So there it is. Okay, so that's it for the 1511 Hamming code. Why is it called the 1511 Hamming code? Because there are 15 positions to store things, okay, which is, if you look at this, we stored it, okay, my figures are a mess, so I'm going to redraw it. Let me just draw it here. 1, 2, 3, 1, 2, 3. So it's called the 1511 Hamming code because there are 15 places to store things. This is all of the 15 places you can store things. We don't store things here. Why? Okay, I want you to figure that out. Why don't we store things here? Yeah, something to think about. And 11 because there's 11 places where you can actually store the message. So the message gets stored in the 11 slots. And that could be, this is the 11 slots. It could be here. Your message could either be stored here, 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 or here. These are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 yellow spots and then the 15 slots altogether. That's the basic idea behind the 1511 Hamming code. Okay. Alright, so that's it from that. Let's move on. The last thing I want to show you is an example of a data security technique. So this is now examinable. I said it wouldn't be examinable in class and I'm correcting it now. This is examinable. It's data security. I'm very excited. I didn't want to leave it out. It's so important. Even if I teach you a silly algorithm like the Caesar cipher, at least you know about some algorithm instead of no algorithm. So the idea behind data security is that you have a sender. Okay, the sender wants to write some plain text. And it's a very affectionate sender. It says, I love you. Okay, our saucy sender. And so what the source sender does is they encrypt this information because they don't want everyone to know. They encrypt with a key. Okay, so they pick a key. The key maybe is a 5, okay? And then you get a ciphertext. The key can be anything, hey? It doesn't have to be a number. So the ciphertext can be something like HY7YU space LT2 hash S. Okay, it's a mixture of lowercase, uppercase, special characters, whatever. Right, so that's what the sender does. So the sender does they do this. So they get some kind of ciphertext with some kind of key, and then the sender then sends the information. So they try to send it through a secure transmission, so there isn't any like possibilities of parity but check flips or whatever. But those things happen anyway, so you have to use data securities in conjunction with error correction. But we're just going to ignore error correction for now. It is very relevant to this, but we're going to ignore it because we're trying to talk about something else. So now you have a secure transmission. I'm going to say this is a secure transmission. A secure transmission of the text XH7YULT2 hash S. Okay, so we sent this information across. So there is a possibility here of interception. So there could be someone who intercepts this message. Okay, so this is where the possibility of interception actually is. So people here, maybe you're sending it over the line and then they intercept the text. So if someone gets this text, they don't have the key either, and they literally have no idea how to decode it, because they'll have to do some code cracking algorithms. They'll have to try a lot of different heuristics and a lot of trial and errors to try to figure out what the text is. So a brilliant person who solved one of the most I want to call it the most emergent problems, because in World War II, when the Germans were sending a lot of these messages, they were doing it using coding systems. And they had something called the Enigma machine that they were using to send messages across the channel from France to Germany and from many parts of the world. I mean, the Germans were fighting with everybody, right? So they were using a special encoding system called the Enigma machine. And a very clever, in fact, the father of computer science solved the problem, figured out how it was. So he was the person on this side, the father of computer science. His name is Alan Turing. He is so relevant to everything we talk about. And you will see that later on in the course when we talk about Turing machines and stuff like that. But here, he was on the other side, and he got messages like this, and he figured out how to intercept these messages and how to decode them. More importantly, how to decode them. So he decoded these messages, and him actually doing that is what led to the Allies winning the war. So it's a pretty big deal. I mean, he was on the other side of this, and he managed to crack it. Not even on the encryption side. So he's a master of cryptography, and a master of many things, as you will see in the course. A very exciting figure in computer science. A very controversial figure as well. But I'll leave you to read the history of Alan Turing, and I promise you won't be sorry. He's a fascinating figure. He's super intelligent, the father of computer science. Everything you're studying here is related to him in some way. A very fascinating figure. Okay, so that's Alan Turing, and more on him later. But for now, let's complete this. So the text then comes onto the other side. So this is now this receiver. And the receiver receives this cipher text. So they get this whole YULT2 hash S. They get this information, and then they put it through a little algorithm to decrypt it. To decrypt with a key. And the key, in this case, he knew what the key was. Maybe they met and they would share the key that way or through another secure way of transmitting the information. And with this key and the ciphertext here from the top, he's able to decrypt it, so he gets the plain text, which was "I love you." Okay, so that's the big idea behind cryptography. This is the problem statement. So the question, what is the problem here? The problem is, how do we get the algorithm, how do we get this algorithm to decrypt and to encrypt? The question marks. That's what we need to do. The key and everything else is the consequence, but what we want is the encryption text so that we can actually the ciphertext to transmit through the line. And we want that ciphertext to be so good that even as someone as smart as Alan Turing is not able to figure out what the message was. And it turns out that there are really sophisticated algorithms to do this now. And one of the most sophisticated ones that we use today is called the RSA cipher. There are others as well, the Diffie-Hellman and all of those. But this one here is one I wanted to teach you because we don't have any time. Maybe you can just Google it and learn more about it on your own. It won't be examinable. But this algorithm is a very powerful one. Okay, so the one that I'm going to teach you, which is examinable, is called the Caesar cipher. And you'll know why we don't use this one. after I show it to you, you'll know exactly why we don't use it. So the Caesar cipher for ASCII texts is represented using the following formula to avoid the first 32 non-printable characters of ASCII. Okay, and the formula is for encryption. It's E of x is equal to x minus 32 plus n modulo 95 plus 32. And I want you to think about, where does this 95 come from? Okay, and where does this 32 come from? Okay, the 32 I think is obvious, right? The 95 is less obvious. I want you to figure out where does that 95 actually come from? Where E of x, please write neatly in your books. I'm very sorry, it's too late for me, but at least your books can look nice. Maybe this is why I never took my own notes. I couldn't read it. Okay, where E of x is the encrypted characters ASCII value, x is the plain text, the plain text characters, ASCII's value, and n is the shift amount. So this is an example of a substitution cipher, because we're substituting one character for another character. And I'll show you an example. Okay, so I'm going to keep going, and then I'll show you an example. So let's say, okay, so this was for encryption, right? To change it into, so this is this part, the sender's part, the encryption. The E of x is here, right? So you're basically putting your x in. Each of the characters is your x, and then you get the ciphertext, E of x. So the x goes in and the EX comes out. And all right, so what about the dx? So the dx, when you get from here, your d of x, to go to the decryption with the key. Well, that there is the decryption. The decryption formula. The decryption formula is d of x, which is equals to x minus 32 and modulo 95 plus 32. So what is different here from the previous one? What is the difference between this formula and this formula? What is the difference? Okay, where d of x is the decrypted character ASCII value. All right, so that's the idea. Super easy. Encrypt using a formula, substitute into the formula, and it's super easy because it's substitution, and your calculator can do this. So what does this mod do? It means divide by 95 and get the remainder. Okay, as a whole number, not as a fraction. So divide and get a whole number, and you get the decryption text. Okay, using the same procedure. Okay, so small arithmetic calculation, a small modulo calculation, and then another basic arithmetic calculation. Use your board mass here if you get confused. Okay, and let's look at an example. So example is encrypt the word secure, all capitals, with a key of 4. Okay, so we have, let's now use a table to do this. So we have a letter. The letter that we have an ASCII value. We always have to try to do things systematically. We have the encrypted ASCII. I feel like I need to write this a bit smaller. Encrypted ASCII. And then finally you have the result letter. So let me draw a line here and a line going down. Okay. We have the word secure. So S E Q C. Oops. U R E. Okay, so I'm going to zoom in a bit so I can write a bit smaller and neater, hopefully. Okay, so what is the ASCII value for S? If you look on the ASCII table, you'll see it's 83. The ASCII value for E is 69. The ASCII value for C is 67. The ASCII value for U is 85. The ASCII value for R is 82. The ASCII value for E is 69. Same as this one. Okay, the encrypted, use the encryption algorithm. It becomes 83 minus 32 plus 4 modulo 95 plus 32, which is equal to 87. Okay, 69 minus 32 plus 4 modulo 95 plus 32. Oops. Plus 32 is equal to 73. Okay, 67 minus 32 plus 4 modulo 95 plus 32 is equal to 71. 85 minus 32 plus 4 modulo 95 plus 32 is equal to 89. 82 minus 32 plus 4 modulo 95 plus 32 is equal to 86. So sorry about that. So 32 plus 4 modulo 95 plus 32 is equal to 73. Okay, so then you go to, how do I go next? Do I go out? Oh, here's a, can do that. Okay, great. So now the resulting letter. All we do here is we just basically write out the resulting letter from the ASCII table. We look up the value and we put in the ASCII value. So I'll do this on another color pen with the purple pen, and I look out 87 in my ASCII table and I end up with a W. I look up 73 and I end up with an I. I look up 71 and I end up with a G. I look up 89 and I end up with a Y. I look up, this is capital by the way, 86 and I end up with a V. And I look up 73 and I end up with an I. Okay, so you can, the shift amount can be any arbitrary value, right? Because no matter what it is, when you modulo, it'll wrap around the table and it'll produce a good result. So what is actually happening here in the Caesar cipher? We're shifting things along. So if you look on your ASCII table and look for the letter S, right? My key here was 4. So that means I've shifted S 4 positions on the ASCII table to get W. I shifted 4 positions from E on the ASCII table to get I. I shifted 4 positions on C to get G. I shifted 4 positions from V to get Y. From U to get Y. This is a U. I shifted 4 positions from R to get a V. And I shifted 4 positions from E to get an I. So look at your ASCII table and figure out that that's actually happening there. The last thing to write the answer is you just say here the resulting ciphertext is therefore WIGYVI with a key of 4. And then this is what happens here. If you go back to that other example here, this is what you get. So we just did a section here. So we for the sender we just put the secure in. The key was 4 and the ciphertext was that WIGYVI, and then now you submit that WIGYVI over the secure transmission. It goes to the receiver. They take that WIGYVI and they apply the key again to it, and they will get secure back. But now I want you to do that. So decode this and see if you get secure with the key of 4. Okay, all right. Yeah, I wasn't bad. It's just 1 hour, and I hope you learned something. So the data security stuff is definitely examinable. Please study it. Just the Caesar cipher for now, but obviously I can give you variants on the Caesar cipher, but obviously in context, right? So but the basic, so what are you learning here when you look at a Caesar cipher, right? You're looking at a substitution cipher. You're looking at shifting things along, okay? And depending on how you change your key will determine the shift that you are dealing with. Okay, so that's what the real learning outcomes are here, right? Understanding how data security actually works, how to apply the formula, how to decrypt, how to encrypt. So it doesn't matter if it's a Caesar cipher. If I give you any cipher, like if I give you something else called the affine cipher, which is also a substitution cipher, which is also about substituting numbers in a formula and getting a shift and then looking up the new stuff in the ASCII table, you should be able to do it too. So the thinking is what's important here. Another thing around the thinking is, where does the cipher fail? And how would someone who gets the text be able to decrypt it? So if someone gets the text, WIGYVI, they encrypt the ciphertext. What kind of algorithm would they use to decrypt something like this? If they know it's a substitution cipher, or if they assume it's a substitution cipher. Right? Try to think beyond what's going on here in terms of the vulnerabilities of the problem, of the encoding scheme, in terms of what kind of keys, what kind of derivations on the encryption can you actually have. Okay, right, good luck everyone. Thanks for watching this till the end.